So AI is advancing rapidly, raising profound questions about sentience, singularity, and AGI. Sentience is about AI. Can AI ever be truly conscious? Singularity is what happens if AI surpasses human intelligence. And AGI is the pursuit of machines that think like humans. First, let's look at sentience. Sentience refers to the ability to perceive, feel, and experience emotions. It implies self-consciousness, subjective experiences, and the capacity to feel pain and pleasure. Current AI lacks true emotions and self-awareness. It can simulate emotions, such as chatbots responding empathetically, but does not truly experience them. So if an AI mimics sentience perfectly, does it matter if it's not real? So this is something people have been discussing about. Again, AI may simulate sentience, but true consciousness remains an open question. Singularity refers to the point where AI surpasses human intelligence and improves itself exponentially. At this point, AI advances beyond human control, potentially reshaping society in unpredictable ways. So there are different possibilities for singularity. One is utopia look. AI can solve global problems, enhances human lives, and eliminated scarcity. A less optimistic outlook is dystopia. That is when AI becomes uncontrollable, leading to economic collapse, job loss, or even existential risk. And somewhere in between, coexistence, AI and human can work together with careful safeguards in place. So there are different views about the timeline for achieving singularity. Some experts predict it could happen within our lifetime. Others argue that true intelligence requires more than just faster computation. The singularity could bring unimaginable progress or existential challenges. It's crucial that we perform careful planning. AGI can learn, reason, and adapt like a human. Unlike current AI, AGI can understand any intellectual task. It can transfer knowledge across domains, and it can adapt and learn with minimal training. So if we compare between narrow AI, which is today's technology, and future AI, which is AGI, in terms of capabilities, narrow AI is specialized, such as playing chess, doing image recognition, self-driving car, and AGI is more general. It can perform any cognitive tasks. In terms of learning process, narrow AI needs massive training for each task, and AGI learns from experience like a human. In terms of flexibility, narrow AI cannot transfer knowledge, while AGI applies knowledge across different domains. So AGI could be as intelligent as a human, but work much faster. And then what will happen after AGI? So it can be a path to the singularity. When AGI is achieved, that is when AGI match human intelligence, then super intelligence emerges. That is when AI surpasses human intelligence and begins self-improving. And then singularity occurs. AI rapidly evolves beyond human comprehension. So is AGI the last invention humans ever ever need to make. If AGI can improve itself, human might no longer need to create new technology. AI could do it all. This could rapidly transform society, leading to either a future of abundance where AI solve all problems, or loss of control where humans no longer govern technology. So AGI is a stepping stone to an unknown future. How we develop it will determine humanity's fate. So sentience is about self-consciousness and subjective experience. AI is not sentient yet. The singularity could be a breakthrough or a risk depending how we prepare for it. AGI is the next major step. If we achieve it, AI will be able to perform any human-level task. Once AGI reaches superintelligence, humans may no longer be the dominant force in innovation. So consciousness is one of the most profound mysteries in science and philosophy. We still don't fully understand human consciousness, so defining what it means for AI is even more complex. So we will explore what consciousness means in human and AI, and different perspectives on whether AI can be conscious. And then we will also explore challenges and ethical considerations of conscious AI. So human consciousness is about self-awareness, subjective experience, and intentionality. Self-consciousness is about knowing one's existence and thinking about one's thoughts. Subjective experience is about feeling emotions, pain, and pleasure. Intentionality is about acting with purpose and decision making. And consciousness in AI is a moving goalpost. Some researchers define AI consciousness as simulation, emotions, and self-consciousness. Some argue it's about displaying intentional behaviors. Or it's about learning and adapting beyond pre-programmed rules. If an AI perfectly mimics consciousness, is it actually conscious? So that is the key question here. And then we also have different views on AI consciousness. The first argument is AI could become conscious. There's this functionalist view that consciousness emerges from complex computation. If a machine processes information like a brain, it may develop self-consciousness. For example, if an AI system learns from experience, adapts, and expresses emotions, how is that different from a conscious being? The second view is AI will never be truly conscious. This is the biological view. Consciousness is deeply tied to organic process, emotions, and bodily experience. AI may simulate but never feel. For example, a robot can say, I'm in pain, but does it truly experience pain or just mimic human reactions? So can intelligence exist without consciousness? There are different views on this topic. Many AI researchers say yes. Some say no. So let's look at challenges in developing conscious AI. If we don't fully understand human consciousness, how can we recreate it in AI? Consciousness may require more than just computation. It may need emotions, experiences, and embodiment. And how do we test if an AI is conscious? So we have Turing test, that is AI mimicking human conversation, doesn't prove self-consciousness. And we have mirror test. Animals recognize themselves in mirrors. Can AI do the same? And there's ethical concerns. If AI becomes conscious, should it have rights? Can we turn off a conscious AI, or would that be equivalent to harming a sentient being? So would we treat conscious AI as a tool, a person, or something else entirely? Looking into future, will AI ever be conscious? So there are possible scenarios. AI may never become conscious. Machines remain advanced tools and can never be self-conscious. Or AI can mimic consciousness. It can appear conscious without but lack real experiences. Another view is AI will achieve true consciousness, a revolution in intelligence, ethics, and society. So there are open questions for science and philosophy. Does consciousness require a physical body, or does it exist in software? Can AI develop a sense of self without human-like emotions? Or would a conscious AI be our equal or something beyond human comprehension? AI consciousness is still hypothetical, but the debate forces us to reconsider what it means to be aware. Human consciousness is still not fully understood, making AI consciousness difficult to define. Some believe AI can become conscious through complex computation, while others say true consciousness requires biological processes. Even if AI mimics sentience, it doesn't mean it actually feels anything. If AI does become conscious, society must address deep ethical questions about AI rights and treatment. The development of AGI requires AI systems that can learn, adapt, and generalize across multiple domains. So we will look at deep learning architectures that power modern AI, and we also examine reinforcement learning strategies for autonomous decision making, and why these techniques are crucial for AGI development. First, let's look at deep learning architecture, which is the foundation of modern AI. First, let's look at convolutional neural network, which is commonly used in vision and pattern recognition. CNN, or convolutional neural networks, are specialized for processing visual data. They identify patterns, textures, and objects in images. They use filters to detect features such as edges, shapes, and textures. Then it applies pooling layers to reduce dimensions while preserving key features. And then it extracts hierarchical features from simple edges to complex objects. Applications include face recognition, medical imaging, self-driving car perception. For sequence processing, deep learning architectures are recurrent neural network or long short-term memory models. So RNN and LSTM can process sequential data. So they are used commonly for language, speech, and time series forecasting. They work by maintaining memory of past inputs, unlike standard neural networks. But RNN struggles with long-term dependencies. LSTM fixes this by storing past information over longer sequences. Applications for RN and LSTM include machine translation, speech recognition, stock market predictions. And then transformers are the power behind large-scale AI. It can handle long-range dependencies and allow models like GPT and BERT to excel in NLP. It uses self-attention to focus on important parts of input sequences. It can process data in parallel, making training much faster than RN. Examples include ChatGPT, automated coding assistants, and search engine optimization. Transformers revolutionize AI by making models scalable and context aware. So reinforcement learning is a very important strategy that leads to decision making for AI. It uses this try and error learning. AI agents interact with an environment, testing actions and learning from the outcomes. A robot learns to walk by repeatedly adjusting its movements. So there are some key components of reinforcement learning. One is policy and value networks. Policy network is for AI learns the best actions to take given a situation. Value network is for AI to estimate the long-term reward of each action. Example of policy and value networks is AlphaGo. It used this policy and value network to outperform human Go champion, a South Korean, Lee Do. Another component is tree search integration, Monte Carlo tree search, MCTS, Monte Carlo tree search. AI explores multiple possible decisions before acting. Chess and Go AI simulates thousands of future moves before making a decision. Reinforcement learning allows AI to improve over time, just like human learning through experience. So why do these methods matter for AGI? So deep learning models extracts meaningful information from raw input, such as which are unstructured data, such as images, speech, text. So they can learn from raw data. This is critical for AGI, which must process a variety of inputs like humans. They can adapt to new tasks and environments. Reinforcement learning enables dynamic interaction. AGI can experiment, make decisions, and learn over time. A general AI could learn multiple games without being retrained. And they can combine deep learning and reinforcement learning. Deep learning extracts patterns. Reinforcement learning makes decisions. Together, they form the foundation for self-learning AGI. So AGI will need both perception, that is deep learning, and action, that is reinforcement learning, to function autonomously. So to summarize, CN process visual data, RN handles sequence, and transformers enable large-scale learning. Reinforcement learning teaches AI to learn from experience like human. Deep learning plus reinforcement learning is key to AGI's ability to learn, adapt, and generalize. AGI must not only recognize patterns, but also plan and make decisions independently. So there are other major approaches in AGI development. One is symbolic AI that focuses on logical reasoning and explainability, and also hybrid models that combine symbolic AI with deep learning for flexibility and pattern recognition. So symbolic AI focus on logic-driven intelligence. Symbolic AI uses formal rules and ontologies to encode knowledge in a structured way. It follows predefined logic, meaning decisions are explainable and predictable. It works well in structured domains such as expert system, legal reasoning, and mathematics. So it has strengths such as explainability and reliability. Every decision can be traced back to clear logical rules. And the outputs are deterministic. The same input always leads to the same result. But this approach also has its limitations. It struggles with unstructured data, such as images, speech, and raw text. It requires extensive human efforts to encode rules for all scenarios. It's not adaptable. It cannot easily learn from raw new examples. Symbolic AI is great for structured reasoning, but lacks adaptability to new situations. And hybrid model may pose the best of both worlds. So hybrid models combines deep learning, which is pattern recognition, and symbolic AI, which is about logical reasoning. It bridges the gap between statistical learning and structured decision making. An AI system that processes raw information, raw image, such as deep learning, and then applies logical reasoning, such as symbolic AI, to analyze the image meaningfully. Examples of hybrid AI applications include robotics, natural language understanding, and medical diagnosis. So in robotics, deep learning processes sensory data, while symbolic logic enables decision making. For natural language understanding, neural network understands text, and symbolic rules ensure logical consistency. In medical diagnosis, AI first detects abnormalities in images, then applies medical knowledge rules to explain results. So hybrid AI systems are more powerful than either approach alone. So hybrid AI may pave the path for general intelligence. AGI must learn from past experience that can be done through learning, deep learning. It needs to reason logically that can be done through symbolic AI. And it needs to adapt to new problems without retraining, that is through hybrid models. So let's look at different challenges and how hybrid AI can solve them. First challenge is lack of explainability in deep learning, and symbolic reasoning in hybrid AI can make AI decisions transparent. For the challenge of symbolic AI struggles with unstructured data, hybrid AI provide deep learning process uh, that can work with raw inputs like images and speeches. For the challenge that AGI requires adaptability and logical reasoning, hybrid AI can combine learning and structured decision making. So hybrid AI models provide a path to AGI by integrating perceptions, learning, and reasoning. So symbolic AI provides structured reasoning but lack adaptability. And deep learning is powerful but lacks explainability. Hybrid models combine learning and reasoning, making them more suitable for AGI. And AGI will likely require a hybrid approach to achieve human-like cognition. So this is a high-level overview of these core methodologies in AGI that we just discussed. So let's focus a little bit more on the reinforcement learning. So it have methods such as Q-learning, which is for AI to learn the best action for each situation. And it use Monte Carlo tree search, MCTS, to explore multiple decisions before acting. It excels in dynamic environment, such as robotics and game playing, and it requires significant computing power and time to train effectively. Reinforcement learning is critical for autonomous AI that learns by experience. Let's look at how large language models can contribute to AGI development. So AGI requires a deep understanding of the world, reasoning across different domains, and adaptability to new situations. Language is one of the most comprehensive repositories of human knowledge, and large language models are a crucial step towards AGI. So we will explore why world knowledge is key to AGI, how large language models can process and store knowledge, and how they can bridge human language with and concepts, and how they can move us closer to AGI. So first, let's look at world knowledge as the foundation of AGI and why is language central to AGI. Language encodes human knowledge. Every book, article, conversation, and video script represents accumulated human intelligence. AGI need to interact and make decisions based on real-world understanding. Language is the key tool for reasoning. And languages are structured knowledge representations. They contain information about science, culture, emotions, and human behaviors. So AGI needs world knowledge, and language is the ultimate knowledge repository. And let's look at how large language models unlock the power of knowledge representation. So large language models are trained on massive data sets from books, websites, and conversations. They create a semantic knowledge map, understanding how words, concepts, and idea relate. Unlike databases, large language models don't just store the facts, they recognize context, meaning, and relationships. So they build a world knowledge map acting as an AGI's brain. We can also use large language models to bridge human language and culture. First, they provide cross-language understanding. Large language models can transfer knowledge across languages, meaning they learn concepts in one language and apply them to another. And large language model trained primarily in English, for example, can still understand Spanish, Chinese, and Arabic due to shared semantic structure. And the role of large language models in knowledge accessibility. Large language models make information available to more people, breaking language barrier. They help improve global communication, education, and collaboration. So a multilingual large language model make AGI more universally intelligent. Now let's explore how large language models can advance AGI capabilities. They can understand context and meaning. They can enable AGI to learn and reason. And they can enhance AGI's decision-making abilities. First, let's look at its understanding of context and meaning. Large language models go beyond keyword matching. They grasp idioms, metaphors, and cultural nuances. They can interpret sentiment and emotional tones, making AI more human-like. For example, it can recognize sarcasm in conversation or distinguish between literal and figurative meanings. And it can enable AGI to learn and reason. So large language models can synthesize information from multiple sources, drawing conclusions like a human. And they provide a foundation for reasoning-based AI models moving towards AGI. An AI lawyer, for example, trained on legal text can answer legal questions with contextual accuracy. They can also enhance AGI's decision-making abilities. Large language models help AI models understand situations, predict consequences, and suggest actions. So AI assistant, for example, in healthcare can provide personalized recommendations based on medical literature. So large language models can bring AGI closer by enabling reasoning, context awareness, and decision-making. So AGI requires word knowledge, and language is the best medium for storing and accessing it. Large language models build a knowledge map capturing the relationships between concepts and ideas. They bridge languages and enables AGI to operate globally. And large language models improve reasoning, contextual understanding, and decision-making, which are the key factors for AGI. While large language models are not yet AGI, they lay the foundation for truly general intelligence.